down the incline. For the slab, you'll need a few things. You need a wood plank for the incline. You'll need a stand to make the angle. You'll need some tin foil to cover the incline so you can protect it from WD-40, which you use as a lubricant to decrease friction. You will also need a meter stick to measure the length and height of the ramp. You will need a ruler to measure the radii of your four objects. Oh, let's not forget the tin foil you need to make rings to prevent some of your balls from rolling when you're trying to slide it. You also need some more WD-40 because you can never be lubed up too much. Use it liberally, just try not to get on your hands. Oh wait, it will. Just wash your hands regularly. You'll also need your four masses. We're using a weighted hoop, a 500 grams cylindrical weight, a golf ball, and a lacrosse ball. Alright, let's go. Alright, let's go to work. Oh, and not to forget a Vernier Lager Pro, hopefully yours will work, and some duct tape to hold everything together. Alright, let's go. So we're going to start with the perfect sliding velocity, and we're going to be using laws of conservation of energy to find our velocity. Let's start with potential energy, PE equals mgh, mass times gravity times height. So we take our mass, 0.44 kilograms, and multiply it with our constant gravity, 9.8 meters per second squared, and our measured height of the release point of the ball, 0.62 meters. Multiply that all together in our magic calculators and we get 2.673 joules. And then also one of the laws is that potential energy, PE, equals kinetic energy of the linear mass, KE sub L. So we set up mgh equal to 1/2 mv squared, and the masses cancel out because they're both the same mass, so that simplifies it a little bit to gh equals 1/2 vl squared. Then we do a little bit of manipulation. We get v sub l squared equal to 2gh, which becomes v sub l equal to the square root of 2gh. We plug in our numbers, and then we get v sub l to be 3.486 meters per second as our perfect world, no friction sliding velocity. But because this is the real world, and despite our greatest efforts to reduce friction with tin foil and WD-40 and whatnot, we do have a considerable amount of friction. So work done by friction, W sub F, is equal to mu sub S times mg cosine theta times d. Make sure this d is parallel to the direction of motion, so I just measure along the distance it slides down your ramp. And mu sub S, the coefficient of friction, is equal to tangent theta of the incline at where the object is first in constant motion. So we found that angle to be 28 degrees, so we substitute theta for 28, and tan theta of 28 is 0.53, which is rather a high number, which is unfortunate. So we get W sub F equal to 0.531 times 0.44 times 9.8 times the cosine of 36, which is the incline of our ramp, times 1.06, which is the distance it traveled, equal to 1.964 joules. And then we go on, now let's go on to our real world sliding velocity, where we have the potential energy minus the work done by friction equal to kinetic energy. And now you've already seen the substitution with moving the equation around, so we're just going to do it. So we have 2.673 minus 1.964 equal to 1/2 of 0.44 times v sub l squared. Move it around and we get v sub l equal to the square root of 3.225, which is 1.796 meters per second. You can see that's almost half of our calculated perfect sliding velocity, so you can tell friction really has a play in here. Now that we have that straightened away, let's move on to perfect rotational velocity. In this, R and V are the same thing because we are using a special hoop that's really known as a torus. It has an inner and outer radius, and the outer radius is R or B in the equation, and the inner is A. We're using R and B as the same because when we substitute out W angular momentum for V squared over R squared, R is supposed to be the contact point with the ramp, which is B. So we have potential energy again, which is mgh, which comes back out to 2.673 joules, which we know is right because it's the same object. And then we have the same concept, potential energy equals the rotational kinetic energy, but because this is rotational kinetic energy, we have mgh equals 1/2 I, the moment of inertia, times w squared, the angular velocity, plus 1/2 mv sub r squared. Then we plug in for moment of inertia and angular velocity, and our equation gets a little messy. We get mgh equals 1/2 times mass over 4 times 4 inner radius squared A plus 3b squared times v sub r squared over r squared plus 1/2 mv sub r squared. Now, because mass is the same in each part of the equation, mass drops out, so we get gh equal to 1/2 v sub r squared times a squared plus 3b squared over 4 times 1 over r squared plus 1, because we also did move the v sub r squared up front, simple factoring. There's also a cool little algebra trick. If you multiply the 1 by r squared over r squared, it helps us simplify it and have one big fraction, so we can rewrite the equation as g times h times 2 equal to a squared plus 3b squared over 4 plus r squared all over r squared, and that quantity times v sub r squared. Now we do a bunch of manipulation to isolate the v squared over r, and then we take the square root and we get v sub r equal to the square root of 2r squared gh over a squared plus 3b squared over 4 plus r squared. We plug in our values that we measured with our handy dandy ruler, and we get v sub r equal to 2.359 meters per second. And if you remember the perfect sliding velocity from before, it is lower than that, showing that in a perfect world setting, the linear velocity of a rotating mass will be lower than a sliding linear velocity of the same mass. So it does work out. Now don't forget, this is the real world, so we have to include work done by friction, which makes it grayer. So we get w sub f equal to u sub s times mg times cosine theta times d parallel. But in this one we measured our mu, we got the theta as 1, so tan of 1 equals 0.017. So once we plug that in for our mu sub s, we get the work done by friction to be 0.063 joules. Now, to just save my sanity, we're just going to do simple plugging in and do the simple arithmetic. So, for potential energy, we get 2.673 minus work done by friction 0.063 equal to 1/2 times m over 4 times 4a squared plus 3b squared times v sub r squared over b squared plus 1/2 mvr squared. Now you plug in the values you have already, except for the v sub r squared. Do some mashing arithmetic. You can do it how you want. You see how we did it. And eventually we get v sub r equal to the square root of 7.045, which becomes 2.654 meters per second. Now you will notice that is higher than the actual velocity of the sliding mass, but that's okay because of the disproportionately large amount of work done by friction on the sliding mass. Now you repeat the process, changing out the moment of inertia for the other objects, and you're good to go.